All right, so if you are watching the video later on today, go ahead and hit pause. Try these 6 questions. They're a good review for the quiz that's going to be coming up this weekend. So I'm going to go through this really quick because you guys had a chance to work through it. And please check your work as we go. So I have 45 degrees. I want to turn that into radians. So I want pi to be back into my answer. So I'm going to multiply by pi over 180. And what we have then is 45 over 180, which pi is just going to stay in the numerator, or you can write it to the side. But if you reduce that, you get 1/4, or pi over 4. All right, so then the next thing is now we have to convert radians to degrees. So we have to get pi out of our answer. There's 2 ways to do it. You could just put 180 right in here and times 5 by 180, or the official way that we had showed you was we need to get rid of the pi, so we're going to multiply by 180 over pi. And that will reduce out the pi's. You multiply straight across, and you end up with, actually, instead of multiplying, this might be a little friendlier. 6 goes into 180, so if I reduce that, it ends up being 30, and 5 times 30 is 150. All right, and then we have to convert a radian measure into degrees. Now notice, how do I know this is radians? It doesn't have a pi. Well, I know it's a radian because it doesn't have a degree symbol. So we're going to do the same work. Take your measure. I want to multiply this by 180 over pi. And again, you can always make this a fraction. And then you're just multiplying straight across. Numerator times numerator, denominator times denominator. And we end up with, let's see, 200. I'm going to do it all at once. I'm going to just, actually, you know what? So if we multiply the numerators together, we get 941.4. And then I'm going to use the pi button. And I always recommend using the pi button. When you divide, don't use 3.14. If you use 3.14, that's rounded automatically, and pi goes on forever. So you want to take the most accurate interpretation of pi, which is using the pi button in our calculator. And then we always recommend rounding to 3 decimals unless the directions tell us otherwise. So you get 299.657 degrees. All right, the next one is find the arc length. And this is the formula we shared the other day. Arc length is a pretty quick formula. It's your radius times the theta. However, theta must be in radians, and that's the thing that we have right here. So notice 72 degrees, we need to turn that into radians first. So I'm going to multiply by pi over 180, just like we did before. And if I reduce that out, theta turns into 2 pi over 5. So that's the first part you need to do with this problem, is change it to radians. And then all you do is multiply the radius, which is 7, by theta. And I might just leave this as an exact answer when I multiply. So what we have is 7 times 2 is 14. Leave pi up top and divide it by 5, and I can't reduce that any further. 14 over 5 stays, so I would leave it just like that. If you actually multiplied it out, I think, actually I didn't do that yet. You can check that out as a decimal here. All right, so there's somebody in here named Chang Lor. If you could, I'm not sure, you're not on my roster, so I'm assuming you logged in as a different name. Can you please just throw me in the text who you are so I can give you the correct attendance for today? Please make sure you check your chat. All right, number 5 and 6. These are the ones that we went over briefly on Monday, and then we said, hey, guess what? You need to know how to do these. This is from Geometry and Algebra 2. It's right triangle trigonometry. So I have 68 degrees, and across from the 68 degrees is the opposite side. X is the adjacent side. So if I'm thinking Sohcahtoa, O and A is the tangent. Now we do have to be careful here in our calculator. We got the tangent of 68 degrees is equal to the opposite over the adjacent. So I usually make this a proportion by putting tangent of 68 over 1. And then I'm going to cross multiply. Or you can just switch the spot of the x and the tangent. But if I did 1 times 13, I get 13. And then I would divide by the tangent of 68. So I'm plugging this into my calculator. You have to be in degrees mode because notice we're dealing with 68 degrees right here. So you need to be in degrees mode. So what is that equal to? When you calculate that out, you should get 5.252 meters, rounded to the third decimal. Right? If you got a different answer, but you did the exact same thing, that just means your calculator was in the wrong mode. All right, and then the last one is we've got to find the value of x. Now notice, x is an angle this time, and we are given the hypotenuse and the adjacent side. So a and h, that is the cosine function. So we're going to use cosine and set up our ratio. So it's cosine of the angle x is equal to the ratio of adjacent over hypotenuse. And then what we need to do is we need to get rid of the cosine and move it over to the other side. The only way to do that is to do the inverse. And this is just a really quick function in your calculator. We shared that the other day. Make sure you're in degrees mode because we want to find the value of x, and it's in degrees. They tell us right there. So if you do the inverse of 6/21, you end up with 73.398 degrees. So if you need any more further explanations, I'm going to post this work when we're done. You can go back and look at it, or you can watch the video and maybe rewatch it as we work through it. All right, today we are going to actually use Sohcahtoa, and the nice thing is the warm-up, the last two problems helped us use Sohcahtoa, but we are going to start introducing the 6 basic trig functions. Now, I'll just let you know that we talked about this last year in Algebra 2, and we did it during the third trimester, which was right when we were in our distant learning. So you may have a little bit of a foggy memory on this, depending on how involved you were during the online learning third trimester. So really pay attention today because we're going to go back through this. It is all based off of Sohcahtoa. And remember, what does Sohcahtoa do? Well, the so is the opposite over the hypotenuse. That gives me the ratio for the sine function. And then we have ka for cosine and t for tangent. But there are 6 total trig functions. So we have the 3 basic, and then we have their reciprocals. And we'll show you that in just a second. All right, so I'm going to give you guys some time to write this down. This is just in general. What if I have a reference angle? Okay, right here. I got theta. Now remember, theta is our symbol. It's kind of like an X, right? It's just a Greek letter that represents an angle measure. And notice, all of these ratios are based off of that same angle measure. So we don't know what this is, but generically, we're going to set up the ratios. And I would recommend that you write it the way that it's written here. Sine, and then cosecant, cosine and secant, and tangent and cotangent. All right, so I'll give you a second to write all this down. Leave some spaces here and here because we're going to write the ratios for each one of them. So let's go over what we have here. And one of the ways that we remembered sine, cosine, and tangent was Sohcahtoa. Actually, maybe I'll write it here. So was the ratio of the opposite side over the hypotenuse. And what always constituted the opposite side was wherever our reference angle was, the opposite was the side that is not touching the angle. All right, and then the hypotenuse is always across from the 90, that's the longest side, and the adjacent was always the side length that made up the angle theta with the hypotenuse. So there's my SO. The ca, or cosine, is the ratio of the adjacent over the hypotenuse. And then toa stood for tangent, and that was the ratio of the opposite over the adjacent. All right, so nothing crazy there. Hopefully you're really familiar with those three. But then we said, well, wait a minute. Each one of sine, cosine, and tangent has a reciprocal. And if you remember, the reciprocal is just taking and flipping it down. So cosecant is officially the hypotenuse over the opposite. And then secant is the reciprocal of cosine, so it's officially the hypotenuse over adjacent. And then cotangent is the reciprocal of tangent, which is the adjacent over the opposite. So we are expecting that you do remember those from third trimester last year. All right, so now we're going to use those, and here's my hint, and this is my way of thinking, and I don't know if it helps, but I think I'm really good with Sohcahtoa, sine, cosine, and tangent. And cotangent is a that one's kind of self-explanatory, right? That just tells you that it's cotangent, so it's the reciprocal of tangent. But how do you remember which one is secant and cosecant, and which goes to sine or cosine? This is my way of doing it. It's a little weird, but I think, well, wait a minute. If I have cosine, C-O-S, and what if I spell that backwards? S-O-C, it spells sock. Well, sock kind of looks like secant, S-E-C. So that's a quick way that I just remember that secant matches with cosine, and that leaves cosecant to match with sine. So I kind of memorize these two, and then I know that the one that's left over goes to sine. All right, so what we're going to do then is we're going to take these newfound ratios and their reciprocals, and we're going to be able to generate all 6 of the trig functions from a right triangle based off of the reference angle theta. Okay, so what I'd like you to do is go ahead and draw this picture right now. And as you're drawing it, we know that we have theta right here. And opposite of angle theta is the side length of 4. And adjacent to theta, the other leg of the right triangle, is 9. And that leaves us to discover or find the hypotenuse. Now, it is recommended that you don't use decimals here. We want to stick with radical numbers. So before I can evaluate all 6 trig functions, I do need to know the value of the hypotenuse. And I have the opposite and the adjacent. Well, those are both legs of a right triangle. So to find the hypotenuse, C, we're going to use Pythagorean Theorem. And then if we need to, we will reduce the radical. So 4 squared is 16. 9 squared is 81. That's going to give me 97. Right? And then if I take the square root of both sides, I get the square root of 97. Now, we should look to see if that reduces. But I think 97 is a prime number that nothing really goes nicely into it. So we're going to leave it as the square root of 97. Okay, so now that we know all sides, here's how I do it, and I strongly recommend doing this if you have all 6 trig functions. I always write it in the same order. Sohcahtoa. Oops, to the tangent, not toa. So I write those first, and then I'm going to write their reciprocals right over here. And this is the way my brain works. If I know tangent, I know cotangent is its reciprocal. And then I know if I spell cosine backwards, that's kind of a very loose way of me remembering that cosine and secant match up. And that leaves just cosecant or sine. So the nice thing about doing this is we know Sohcahtoa, right? Opposite over hypotenuse, adjacent over hypotenuse, and opposite over adjacent. So I already have all my side lengths labeled. So the opposite side is 4. The hypotenuse is square root of 97. Now I know right away you're thinking in geometry, we never really liked this square root on the bottom. We're going to deal with that in a second. I'll show why I don't want to deal with it yet. All right. And then the adjacent is 9, and the hypotenuse is the square root of 97. The opposite is 4, and the adjacent is 9. So we don't really like the way the sine and cosine ratio is written right now, but don't change it yet. And the reason why is because if I know sine, cosine, and tangent, their reciprocals are really quick and friendly. So what is cosecant? Well, cosecant is the hypotenuse over the opposite. So I'm just going to flip the sine fraction ratio upside down. And then same thing here. Secant is hypotenuse over adjacent. So it's going to be the square root of 97 over 9. And cotangent is adjacent over opposite, so I'll flip 9/4. So let's say we're doing this in Delta Math and they tell me to write the sine ratio. They probably won't accept 4 over square roots of 97. So I'm just going to move these over. We have to deal with reducing the radical for these.
Hey, do we have to share our triangle or no? We don't have to, right?
You have to share it. We have everything set. We just have to reduce this fraction. And when we reduce the fraction, the square root of 97 has to be changed. So the only way to undo the square root is to take the multiply by the square root of 97 in the denominator. So when I do that, down here, we get the square root times the square root, which is really the same thing as squaring it, so that reduces out. And this is not a super friendly format, but notice if I did that right away, and then I tried to flip it that made this problem extremely challenging because I'd have a radical in the denominator again. So that's why we do it at the end once you have the reciprocal relationships already written. Okay, and then this one is the same thing. To get rid of the square root on the bottom, we times by the square root of 97, top and bottom. And that's the only two that have to be reduced because the other ones have the radicals in the numerator or they don't have them at all. Okay, so that's our goal to start, is just really get used to those reciprocal relationships. Now, I want to go over this one really quick. I don't want you to write it. All right, so what I want you to do then is I want you to just kind of take a look at what's given. They tell us the ratio of cotangent, and then they say find all the other trig values. Well, what I'm thinking of is this. I'm thinking, what do I know? Right? I know that the sine, cosine, and tangent were all the ones that we had before, right? That was the opposite over hypotenuse. That's the adjacent over hypotenuse, and tangent was opposite over adjacent. But they give me cosine. So I'm going to go over here, or excuse me, they give me cotangent, and they tell me that cotangent is 6 over 5. Well, wait a minute. Cotangent is the adjacent over the opposite. So I actually know that this side length right here is the adjacent, and the side length for 5 is the opposite. So from that alone, I could draw a triangle, or a right triangle. But notice, if I know cotangent, I'm just going to flip that around, and I automatically know tangent. Okay, so then the next one I could find out is maybe secant. And secant is the hypotenuse over the adjacent. And that leaves cosecant as the hypotenuse over the opposite. So all the rest of these involve the hypotenuse, and you technically, once you really get good at this, you don't need a picture, but I recommend drawing it. And it doesn't have to be super accurate. I'm just going to say, here's my right triangle, and the opposite side has to be 5. And the adjacent side has to be 6. And that leaves the hypotenuse, which we have to find. And it's the same way we did before. Pythagorean Theorem. We get 61, and c equals to the square root of 61. I don't think 61 reduces down, so I'm just going to leave it as a square root of 61. And then I can set up all the ratios. So since the hypotenuse is under the square root, I know these ones over here are going to be really quick. Hypotenuse over opposite, so that's square root of 61 over 5. Hypotenuse over adjacent, that's square root of 61 over 6. And then I have my reciprocals, so I can just flip these. This is 6 over square root of 61, and then this one would be 5 over square root of 61. But I do know that I'm not happy with these two answers because they're the only ones that have the radical in the bottom. So I'm just going to, nope, not going to do that. I'm going to multiply the top and the bottom by the square root of 61. So I get 5 square roots of 61 over 61. So hopefully you remember reducing the denominators in geometry. And we did that a little bit in Algebra 2 as well. But it's a pretty quick process. So look at what we did. given one ratio, in this case it was cotangent, we knew the adjacent and the opposite, so I drew my picture. I found the missing hypotenuse side, and then I was able to set up all other trig functions. So I'm going to let you go ahead and do that. My only hint to you guys is before you start, set it up in the same way every single time, right? Sine, cosine, tangent. So those are my original functions, and then do their reciprocals. Cotangent, I spell cosine backwards, that's secant. And then cosecant is left over. All right, so I'm going to let you guys try this. And we'll come back in about 2 minutes. Okay, so let's go over this quick. I kind of filled out some things. So I'm thinking Sohcahtoa tells me the ratios for sine, cosine, and tangent, which then automatically gives me the reciprocal relationships for cosecant, secant, cotangent. Well, they give me cosecant. So I'm thinking, okay, cosecant is the ratio of hypotenuse over opposite. So that means the 3 is the hypotenuse, and the opposite side, the one across from the reference angle, is 2. It really doesn't matter how you draw your triangle, as long as whatever angle I call theta, 2 is the opposite of it, and 3 is always across from the 90. So now, I just need to do a little side work to find the missing side length here, which is the adjacent side. Well, we have Pythagorean Theorem, so the hypotenuse squared has to equal the sum of the other two sides squared. Since this is adjacent, I'll call it A. And then it's just some quick algebra. 3 squared, 4 squared, 3 squared is 9, 2 squared is 4. A squared, subtract 4. And I get the square root of 5, which does not reduce down. So we're going to leave it. And that is the missing side length that we need to figure out all the other answers. So I should have started with the easiest one, right? Cosecant is 3 over 2, which automatically then puts sine as 2/3, because those are reciprocals. And now that I know the adjacent, oops, I wrote this one wrong. So secant is hypotenuse over adjacent. Now notice, that has a square root in the bottom. So I don't want to simplify that yet. I want to first go ahead and flip it. So I have the adjacent over the hypotenuse here. I'm okay with this answer if the square root is in the numerator, but here we have to multiply by the square root of 5, top and bottom, and that will give me 3 square roots of 5 over 5. Now, some of you might be wondering, this is a really friendly example to do it. Why does the square root of 5 times the square root of 5 turn into just 5? Well, square root of 5 times square root of 5 is the square root of 25, and the square root of 25 is 5. So that's why we multiply by the square root of 5 here, is that'll reduce the square root in the denominator. All right, and then we can do cotangent and tangent pretty quickly. Tangent is opposite over adjacent. So that's 2 over square root 5. But before I simplify that, I'm going to bring the reciprocal over here and say cotangent is square root of 5 over 2. And then I should just go back to tangent and simplify that one. So I get 2 square roots of 5 over 5. Now, I do want to point out we are setting the foundation for being able to do trig functions and being able to solve these problems. So there's a reason why we're doing all 6 of these. And one of those reasons is you really make a strong connection to what are the reciprocals. We hope Sohcahtoa is is in your brain and you know it very well. So then all you have to do is kind of memorize which ones are the reciprocals. Okay, so here's another problem. I don't know if you want to write down all of this. Here's what I would do. I would write down this part. This is given, right? So they tell us that the sine of some angle A is 7 over the square root of 65. Now, you might argue, and I would agree, we don't really love that square root of 65 as is, but we're going to leave it because that's the way that it was written. And this is sine. Well, sine is the opposite over the hypotenuse. So we know the opposite in the hypotenuse, and it is in quadrant 1. I will just kind of mention everything we're going to be doing is in quadrant 1 to start. So think about an XY plane. And this is saying that if I went, this might not be an accurate triangle, but it's fine. Here's angle A right here. It's the same as if I called it theta. Right? And what we know is we know that the opposite side is 7, and the hypotenuse is the square root of 65. And that's what this triangle would kind of look like in quadrant 1. So then we have to find the exact value of secant of A. Well, I'm thinking, what do I know? And what do I need to figure out? So we know we have the opposite over the hypotenuse. And I know that if I spell secant backwards, that's cosine. And cosine is the adjacent over the hypotenuse. So I don't care about this answer. I care about the reciprocal of that answer. So that's what gets me to the ratio of hypotenuse over adjacent. And that will give me the answer to this value. Right? So I know the hypotenuse. That's 65. What I don't know is the adjacent. So in this problem, we don't have to write out all 6 relationships. I use sine, and then I use the fact that secant is the reciprocal of cosine, so I need adjacent and hypotenuse to fill that ratio in. Well, we're going to do Pythagorean Theorem. And I'll call A the adjacent side, and then B is 7. And the nice thing here, the square root squared goes away, so this is just 65. And then we get 7 squared is 49. If I subtract, we end up with 16. And the square root of 16 is 4. All right, so Pythagorean theorem allowed me to find the adjacent side, and then the answer we're looking for, find the exact value of secant of A. That's the ratio of hypotenuse over adjacent, and here is the overall answer. That's the exact value of secant of A. So very similar to what we did, except for you use one function to find another. Okay, so why are we doing this, right? What's the big reason why I need to figure out all these relationships for all 6 trig functions? Well, I'll show you here. And there's a way that we can solve these relationships together. So you may really want to write this next slide down. It depends. My experience is most students end up forgetting about the special right triangles from geometry. And different teachers teach them in different ways. So I teach these and we use these in calculus almost twice a week, maybe 10 times a week, depending on the content that we're doing. So this material never goes away. and it's going to be the basis for what we're doing next week. So what we want to do is we want to start off with a special right triangle. And we have two of them. We have the 45-45-90 triangle or the 30-60-90 triangle. And it doesn't matter how you draw your picture. But we want to start off with the 45-45-90. All right, now, something from geometry, if the side lengths opposite of the angles, if the angles are congruent, those are base angles, that means that the side lengths are congruent. So that's in my mind, that's a really big piece to help me memorize this. This is an isosceles right triangle. And we are going to be basing things off of a side length of 1. So if I have a side length of 1 and 1, I could do Pythagorean theorem here. 1 squared plus 1 squared is 2, and then 2 would equal c squared. So if I took the square root of that, here's my side length. Okay, these are very important side lengths. 1, 1, square root 2 for a 45-45-90. Okay. Now, for the 30-60-90, you can draw this in many different ways. It doesn't really matter, but I'm going to draw it this way. And I should share that this came from an equilateral triangle where each side length was a length of 2. So picture, I'm going to erase this, but picture the exact same size triangle over here. So this side is 2 and the entire bottom is 2. Well, that makes this side 1. And what's important about that is if it was definitely an equilateral triangle, this would be 60 degrees. This angle is cut in half, so it's 30. And then if I dropped an altitude, that would be 90. So there's a reason why and where this came from, and hopefully you saw that in algebra or geometry. But we're really just focused on this special right triangle. And so across from the 30 is 1. 30 is the smallest angle, so it's going to get the shortest side. 90 is the largest angle, and it's going to get the largest side, so that's a really quick way to remember where the 1 and the 2 go. But where does the number, what goes here? Well, you don't have to write this, but here's some side work. What if I did Pythagorean theorem? Right? My hypotenuse is 2, so I get 2 squared equals 1 squared plus b squared, and then I subtract 1, and then I take the square root. The missing side length, the side length that always goes across from the 60, is square root 3. So you will be asked to memorize these two triangles. And as I tell you, my calculus kids use these all the time. So what's a good way to remember this one? I think 1, 2, square root 3. 1 is the largest side, or excuse me, the smallest side. It's across from the smallest angle. 2 is the largest side, and it's across from the largest angle. And then always across from the 60 is the square root of 3. Okay. Now, I don't know if you want to write this, but if I was to convert, think of our warm-up. We converted 45 into radians, and 45 was the same as pi over 4. How do I know that? If I take 180, which is the same as pi, and I divide pi, or 180, into 4 equal chunks, I get 45 degrees. So here's an example that you could be given this picture as well and still have to be able to identify what side lengths go where. Well, pi over 4 and pi over 4 are going to have the same sides. So 1, 1, and then always across from the 90 degrees is a 2. So here's the other special right triangle that you could use. Notice they're exactly the same. And then if we look at the 30-60-90, the 30-60-90, well, picture this. If I take pi over 6, a quick conversion for pi over 6 is to take and replace pi with 180. And 180 divided into 6 equal pieces is 30. So here's my 30-degree angle. And if that's 30, 60, 90, pi divided by 3 is 60. So these are equal or equivalent. So then what goes across from the 30? Well, always across from the smallest angle is 1. Always across from the 90 is 2. And always across from the 60, or pi over 3, is square root 3. Okay. Now, we are going to be redrawing these pictures probably 100 times in the next 2 weeks. So you will, almost by force, have to memorize these. Okay, so we got 2 more slides here, and then you guys are done. Well, let's look at using these. If it's in radians or degrees, it doesn't matter because the numbers are the same. Let's look at a problem like this. Okay, now you don't have to write out all of this. It says, let's evaluate the 6 trig functions. So now we want to figure out what is the actual numeric answer for sine, cosine, tangent, all of them at theta is pi over 3. So here's the way my brain works. Before I do anything, I'm thinking pi over 3. Well, wait a minute. Pi is the same as 180, right? And 180 divided by 3 is 60 degrees. So when I say theta is pi over 3, that's the same as the 60-degree angle. So we're going to draw a right triangle, and the angle that's larger is going to be pi over 3. That's 60. And then the angle that's smaller is pi over 6, which is 30. And now I have, if you want to write the degrees in, you can. That's 30. That's 60. But the very first thing I'm going to do is go across from the 30 and put a 1. And then across from the 90 is a 2. And always across from the 60-degree angle is square root 3. 1, 2, square root 3. That's how a 30, 60, 90 works. But they tell us that I want to evaluate all of these trig functions. So I want sine of theta, but theta is pi over 3. And I want cosine of pi over 3. I want tangent of pi over 3. And then I want their reciprocals. So this is the way my brain works. I know the easy one for me is tangent and cotangent are reciprocals. Notice the angle measure stays the same. It's always of the reference angle pi over 3. And then we've got, if I spell cosine backwards, that's like secant. And then the one that's left over is cosecant. That's the reciprocal of sine. All right, well, since sine is opposite over hypotenuse, that's the so. Cosine is adjacent over hypotenuse, that's the ca. And toa is opposite over adjacent, that's tangent. I'm going to set up the functions I know already and then just write the reciprocals because these are all really pretty friendly numbers. So the question is, which one is my opposite and which one's my adjacent? Well, that is based off of the reference angle. All of these are based off of pi over 3. So I'm going to follow across from the reference angle that we were told to use. That's the opposite side. Hypotenuse is the easy one to find. And then that leaves 1 being the adjacent, which is the one that's connected to the angle. And now it's really quick. Right? We have all 3 sides, so we don't have to do Pythagorean Theorem. And we know what the opposite is. Opposite over hypotenuse. The sine of pi over 3 is equal to the ratio of the square root of 3 over 2. Cosine is adjacent over hypotenuse, so that's equal to the ratio of 1/2. And tangent is the ratio of opposite over adjacent. Now, you could, because this one is a little unique, I'm not going to write it yet, but instead of writing square root of 3 over 1, you could really just call that square root 3, and those would be the same. Okay, now that you have the 3 easy ones, sine, cosine, and tangent, the reciprocals are pretty quick. We're going to flip square root of 3 over 2, but we want to change that appropriately. So I'm going to move the square root of 3 out of the bottom, and I get 2 square root of 3 over 3. Secant of pi over 3 is the reciprocal of cosine, so that's just 2 over 1, or we can just call that 2. Okay, and then the last one is flipping tangent upside down. But what I would do is change that to square root 3 over 3 on the bottom. And you don't need the 1 out front, so we could just call that square root 3 over 3. All right, so very similar things that we did. The only difference now is if they give you an angle measure that's a 30, 60, or a 45, or the radian measures, you need to use the special right triangle to set those up. All right, we have one last problem, or one last page here, and then we're done. And we might not get through all of this problem, which is fine. But this is the big step. And I will just tell you, my kids coming into calculus struggle solving these. And there's multiple ways to do it, multiple ways that teachers teach it. So I'm going to teach you one way, and I'll show you another way on Monday, and you might like the way on Monday better than what we have here today. All right, so let's look at what they tell us. Find the exact value of sine of pi over 6. Express your answer with a rational denominator, meaning we don't want square roots in the bottom. So here's the way my brain works. Pi over 6. The first thing I'm going to think of is, well, what is pi over 6? Pi is the same as 180 degrees. So if I take 180 and divide it by 6, this is the exact same thing as asking me to solve what is the sine of 30 degrees. Those are the same. So what I need to do then is I just need to draw a picture. And I'm going to put it in the coordinate plane because eventually that's where we're headed, is everything is going to be in one of the quadrants. So think about where 30 degrees would be. 30 degrees would be just up here a little bit. Right? So this angle right here is 30 degrees. But we really are making references to pi over 6. So if that's 30, then this angle has to be 60, and we know 90. And now comes the memorization piece. Across from the 30 is a 1. Across from the 90 is a 2. And across from the 60 is the square root 3. So all of the angles that we're going to be working with over the next couple of weeks are 30, 60, or 45s. So now the question is what is the ratio of sine at pi over 6? Well, Sohcahtoa tells me what sine is. I just need the opposite side over the hypotenuse, and we're done. Okay. So that's the question is, well, which side is technically the opposite? If my angle of reference is 30, and I go opposite of that, there's a 1. And that leaves the one across from the 90 is the hypotenuse. So opposite over hypotenuse is 1/2, and that is the exact value of sine of pi over 6. Now here's the nice thing. Once you do one of these problems, and we only have 5 minutes left, so I'm going to do this quick. I don't know if you want to write this, but now they tell me to do tangent of pi over 6. Wait a minute. Tangent is the TOA. That's the opposite over adjacent, but I'm still looking at that exact same reference angle. So why draw a whole new picture when I have everything all here, right here? I just need to pick the opposite side, which is 1, over the adjacent side. So opposite over adjacent, but we don't like that answer. So if I times the bottom and top by square root 3, I end up with square root 3 over 3 with my answer. And all of that just came from knowing this right triangle. All right, last one. And it's up to you if you want to write this one down. But here's the way my brain works. Okay, cosecant, that is the reciprocal of sine. And if sine is the opposite over hypotenuse, this is equal to hypotenuse over opposite. So my final answer is the cosecant of pi over 6. Now notice it's the exact same angle. I need the hypotenuse, which is 2, over the opposite, which is 1, and we're done. Okay, so it's going to take a lot of practice to get there. This stuff is, the hardest part is memorizing the 30, 60, 90 triangles and the 45, 45, 90. All right, so here's what we got. You have a quiz today. It's a sign today, but it's not due until Sunday, so you got some time to work on it. But you also have a Delta Math homework tonight. So the Delta Math homework is due tonight. It's 4.2. It deals with setting up the 6 trig functions like we talked about. And then if you want, you could do the quiz as well. And the warm-up that we just did will prepare you for that quiz pretty easily. I'll be available in my office hours from 1 to 2. If you have any questions, please stop on by. Otherwise, have a great day, and we will see you next week.